Okay, so I'm picking up from yesterday where we started looking at central limit theorems and large deviation principles for Julia. We looked at the deterministic case where you had a single map and showed how you can estimate the variance and the rate function for an observable. And we went through a little code and talked about stability and perturbation theory. And now I want to switch to the random setting. So the setting now is that we have a potentially random or time-dependent observation, G. And we're back in this random or time-dependent co-cycle of maps. And the first thing you might ask is, why a random G? So random G, there are a couple of ways to look at it. So there might be some systematic or time-dependent bias that the measurement has over time. Or if this is really random, then Steve in his talk, actually, I think he was giving the talk in this room, he talked about, I think he used different terms, but dynamic noise and observational or measurement noise. So dynamic noise is something that we build into the co-cycle. That's what the omega is doing here. That's why we have the map co-cycle. That's the dynamic noise that acts in the state space. And you can have measurement noise, and the measurement noise can be captured by the omega dependence of the G. So the measurement noise might be something simple like IID, adjustments to your measurement, or it could be something with longer memory. So our sigma, remember, this is just ergodic, it's not Markov or Bernoulli, so you can essentially have your noise on your measurements being caused by any stochastic process, any ergodic stochastic process. Okay, now in the deterministic case, I started off saying without loss of generality, we subtract the mean from the observation, and I'm going to do the same thing here. So we'll do this fiber-wise. So for each omega fiber, I'm going to subtract the G omega mean. Okay, this is again without loss of generality. This is not too big a thing to do. And it makes the formulae a little cleaner. So I'll define the non-random variance, sigma G squared, using the same notation, to be this expression here, which is an analog of what we had in the deterministic case. So let me remind you of what we had in the deterministic case. We had sigma G defined here. Okay, I'm sorry, that was the Sn. We had sigma G defined here. And I noted at the time that this is just the usual expression for the variance of a sum of dependent random variables. So nothing very mysterious about it. The n here was coming from the root n that you do for the central limit theorem scaling. What I'm doing now in the random case is completely analogous. I still have this integral over space of our square of our Birkhoff sum, random now. What I'm integrating against now is not just a fixed mu, but it's a mu depending on omega. And then finally, I take an expectation over the omegas with p. So in the end, I have some non-random variance. And the theorems I'll have later, they'll have non-random variances. So the ergodicity in the driving will mean that if you observe long enough, the variance you see even in your random central limit theorem will still be non-random. Okay, so now let's see how we set up the operators. This is in analogy to what we had last lecture. I had last lecture a twist, LZ, or Z. I don't know why I'm saying Z in the UK. And that was just e to the Z G, F in the deterministic case, but now we have our random G, we have our random operator, so I've just put essentially omegas in 3 places here. It's the same as yesterday. Now we iterate this twisted co-cycle in the usual way by concatenating along our omega orbit. And in the deterministic case, I had the leading eigenvalue lambda as a function of z. Now I'm going to have the top Lyapunov exponent as a function of z. So lambda star was what we called the top Lyapunov exponent. It's non-random, but now it's a function of z. Now it's a function of the twist. Your index of compactness is also non-random, but it's a function of the twist. Okay, so now, yeah, how do you, I mean, I'm not going to go into details, but let me sketch how this would go. It goes analogous to the deterministic case. So as in the deterministic case, we show that for small z, if we had a quasi-compact untwisted cocycle, we have a quasi-compact twisted cycle. The top Lyapunov exponent is a twice continuously differentiable function of z, similar to the deterministic case where we had a twice continuously differentiable leading eigenvalue. And this Lyapunov exponent is convex in a small neighborhood of 0. Okay, and the way we get this is, well, we have to build it's built on perturbation theory for linear operators. We build a random implicit function theorem, and we combine this with the multiplicative ergodic theory machinery. Okay, and so I will end this section by summarizing the two main results. So here is the quench central limit theorem for your random dynamics. So assume you have one of these admissible cocycles. I've left out the hypotheses because it's essentially the same hypotheses we've been talking about all the time. Assume your non-random variance is positive, then you have that your random Birkhoff sums scaled by root n converge to a normal in distribution. And so what I'm saying is I show convergence in distribution by testing against every bounded continuous f. So the limit of these numbers converges to this number, and this is in an almost every sense. So you pick a fiber omega, you run out your statistics, and for every single realization of the noise or the time dependence, you converge to the same normal with the same variance because of the ergodicity of the driving. Okay, the quench large deviations, this looks similar. So now remember Z star is our threshold, sorry, our range of thresholds. So for S in this range of thresholds, we want to check if our Birkhoff average, now random, is above the threshold. I've subtracted the mean, remember, so if I make these random Birkhoff sums by Birkhoff, I should be getting close to 0. What's the likelihood that I'm above some threshold? That will decay exponentially quickly, given by this limit. And the rate of decay, the rate of exponential decay is a function of the threshold. And that function is the rate function. And the rate function here is, it has all the usual properties in the deterministic case, non-negative, continuous, convex, vanishing only at 0. It's non-random, okay? So again, for almost every omega, so you start in some driving configuration, you compute your large deviations, and the rate of decrease of this bad set is exponentially fast according to some non-random function. Okay, and okay, this is a note that similar random CLTs and LDPs were previously proved by other means, and what is new here is the spectral construction, which leads to a quite elegant, in our opinion, way to demonstrate things. Yes.
Was there a martingale assumption above the integral? I mean, there wasn't, right? It's only the integral over the fiber itself.
Yes, the integral on the fibers. Yeah, but this is not super important. It's really the quasi-compactness that is driving everything. Okay, now I'm not going to be able to complete all of the lecture notes in the remaining time, so I had to make a decision what to cut out, and what I'm going to cut out is a little bit of open dynamics. So I'll do some open dynamics, enough to set up the next two subsections. Sorry about that. But it's better to have, I guess, too much than too little. So up until now, we've been talking about dynamics that operates on the phase space, and trajectories just go around your phase space. Now I want to think about the situation where you have a hole, and trajectories, if they enter the hole, will vanish and the trajectory terminates, and that's it. So in such a situation, you may not even have an invariant measure, and often you don't. So in the usual setting for closed dynamical systems. And here in this section, I'm introducing some new notation, which is a little unfortunate since I'm cutting a lot of this section out now. But here in this section, TC is going to be the closed map, so C for closed, and the T without the subscript is the open map. I also changed the what I called previously mu to eta, because I had a lot of etas coming later, but now there are going to be fewer etas, so sorry about that again. But in the closed setting, we're always interested in these invariant measures. In the open setting, you may not have them. For example, I mean, think of a circle rotation, and you put a hole in a segment of the circle, and if your rotation is irrational, then everything falls in the hole, and everything is gone eventually. So that's not a very interesting situation. What you can hope for is a conditionally invariant measure. So you have, if you ignore this part for the moment, then this is your usual invariance condition. And what you can do is you can say, okay, when I push forward the measure, I'm going to lose something, so I scale it down by some number between 0 and 1. So this is between 0 and 1. And maybe this example is good to keep in mind. So let's say you have the tripling map on the unit interval. You put a hole in the middle branch. So if I draw a graph of this, that has slope 3, then I skip a branch, and then I have slope 3 again. This is 1/3, this is 2/3, this is 1. So this is a graph of T. And Lebesgue is the conditional invariant measure for this open map. If you take Lebesgue and you push it forward, you have these lovely 2 full branches. So Lebesgue gets stretched twice over the interval, but your slope is 3 and you're losing 1/3 of it. So you have that the push forward of Lebesgue evaluated on the unit interval is 2/3. So you push and you scale down by a factor 2/3, reflecting that you lost 1/3 of your Lebesgue measure. So I think this is a nice mental model to have in mind. And if you, in general, if you control how much phase space can escape into the hole, how quickly the intervals that are partially leaving grow, at the rate at which mass is falling in the hole, you can construct a set of hypotheses for which you get absolutely continuous conditional invariant measures, which is this summary coming up here, which I think I may skip due to time. But let me just finish with a few more relevant constructions for later. So I didn't highlight what x0 was, but x0 is the complement of the hole. And you can define xn to be, so x0 is, okay, after doing nothing, I didn't fall in the hole. And xn is, after n iterations, I still didn't fall in the hole. I survived for n steps. So xn is getting smaller and smaller with n. And then you can let n go to infinity, and you have the set x infinity, which is the set of points that never fall in the hole. So this is the infinite time survivor set, or just survivor set. And you can, in this setup that I was going to talk about, you can have a probability measure eta infinity on the survivor set. This can be invariant under the open map, because all the points are going to survive forever. So it makes sense to talk about an invariant measure. And the escape rate rho, which I'm going to talk a little about later, that rho is this quantity here. So in this case, rho would be 2/3. It's called the escape rate. It's a little weird name because it's based on the fraction that remains in the domain. I always find it a little counterintuitive to call it escape rate. Okay, the last thing I need is the open transfer operator. And this is defined in terms of the closed one in a very natural way. So LC is my closed transfer operator corresponding to TC, closed map. And to get the open transfer operator, what I do is I just take my argument f and I multiply with indicator on x0. So all this is doing is just zeroing out anything that was in any part of F that was in the hole. And then you apply the usual transfer operator. That's it. So you zero what's in the hole and you push. And then if you iterate again, you zero what's now in the hole and then you push. And so things that will be pushed into the hole, they gradually get zeroed out along the trajectory. And so if you iterate n times with this open transfer operator, this is the same as multiplying by the indicator on the points that survive for n minus 1 steps. Okay, so I think I'm going to skip ahead a lot now, and you can in these settings do rigorous approximation as well. So you can apply Ulam to this open dynamical system, and you can construct convergent estimates of the conditional invariant measure and the quasi-conformal measure, which I didn't talk about here, but Jeroen talked about yesterday if you were at his talk. There was some code for you to do that. Maybe just a couple of applications. So I guess nowadays everyone is aware that there's plastic garbage patches in the ocean. And you can view these as an application of open dynamics, because what happens is the garbage is floating around on the surface, and there are points of convergence where on the surface of the ocean where the ocean is, the flow is descending. And so from the point of view of the surface, it's a hole, because you have the water is leaving the surface and descending. And so in this experiment, what we did is initialized with a pulse of garbage around the coastlines of all the countries of the world, according to their population, proportional to their population. And then we used the transfer operator based on the ocean currents to advect forward thousands of years. This shows something after 10 years. And after very short periods of time, you get this, what was once on the coastline move into these well-known patches, and you can get some estimates of concentration. The complement of the survivor set, so you can think of the survivor set as the complement of the survivor set, you can think of this as the basin of attraction of the whole. Yeah. And so you can then estimate these basins of attraction for the five garbage patches, and you can then pick up meaningful divisions in the basins of attraction. For example, along here, depending on whether you're just a little to the south or north of this corner of Southwest Australia, you either go into the South Pacific or you go into the Indian. And similarly around South Africa, if you're a little lower, you go into the Indian. If you're a little higher, you go into the South Atlantic. So when we wrote this, the quality is a little strange. It's the National Geographic picture. When we wrote this, we pitched this as redrawing scientifically the boundaries of the major oceans based on currents, because the political boundaries are, you can see this faint line here. So what delineates the South Atlantic from the Indian is this north-south line, and what delineates the Indian from the South Pacific is you pick a point on Tasmania and you go down to Antarctica. So they're just kind of arbitrary boundaries of oceans that have no relation to what the actual currents are doing. And these boundaries, on the other hand, are also minimal transport boundaries. So often they coincide, so you have these equatorial currents that make sense according to the political boundaries, but at least in the southern hemisphere, there are a lot of boundaries that don't really make sense, but these are much more sensible. Okay, so now I will skip ahead to, what am I skipping? I'm skipping, yes? Yeah. Yeah, they're pretty big, but they're also very, what's the opposite of dense? Sparse, I guess, sparse. So, yeah, I mean, if you took a swim through them, yeah, it's just that it's not like a big island of garbage that accumulated. It's just the concentration of the plastic is very high. relative to having nothing, and so you can still swim through these things, and they're often little tiny pieces, right? Because the waves and the sun break them up, and it's super hard to get these little pieces out. Yeah. So they do cover large areas, but they're sparse, for want of a better word. I mean, no, probably not. I mean, sometimes there are big pieces that haven't broken down yet, but a lot of the time it's just little pieces floating in the ocean, and it is hard to see. So the way they find them is by trawling. Actually, after we wrote this paper, a year or two later, people were taking nets behind boats to estimate what is the concentration, and the concentration pictures matched pretty well with what we had. So seems accurate, at least for the bits that they surveyed.
But they were found, right, by a sailor, so there's something missing, right?
Oh yeah, yes, they were known for some time, and I don't know the exact history of how they were. I guess some people saw the big pieces, and then, yeah, I don't know the history of how people initially surveyed them. Yeah, I mean, these were also, these regions of convergence are also well known to sailors for a long, long time. It's just now that it has this plastic consequence as well. Yeah, what am I skipping? I'm skipping a theorem by Livrani and Momme-Deschamps for existence of a bunch of measures that are connected with open dynamics in the deterministic setting, and I'm skipping, in the random case, a corresponding existence theorem joint with Cecilia and Sandra Vajenti and Jason Atnip for all these random analogs. Okay, so now I want to move to extreme value theory, and if you're not familiar with this, let me start with something. Sorry if you are familiar with it, this will be maybe boring, but suppose you just have some IID random variables, psi1 up to psi n, so they're all distributed the same and they're independent. And you make a new random variable, which is the maximum of the ones you've seen so far. And you'd like to know, given some threshold, which can vary with the number of observations you're making, increasing, what is the probability that you didn't exceed your threshold at time n? So in this easy IID case, you can calculate this explicitly. So the likelihood that you didn't exceed your threshold is just the product of all the individual probabilities by independence and identical distribution. Of course, by complementing, I could write it like this: 1 minus the probability that you did exceed. And now, if we scale these small I did exceed probabilities, like t over n for some t that you pick, then this probability becomes, well, this is just what I had before, and now I substitute in here the t on n, and now by first year analysis you get e to the minus t. So this is the very basic extreme value law, and for the IID case it's called the Gumbel law. Okay, now let's think about extending this to deterministic dynamics. So we have some observation h on our phase space, and we're going to record observations along the trajectory like we did for the central limit theorem and the large deviation principle. So the random variables h composed with t to the j take the place of psi to the j. And if we're chaotic, then if you have a j1 and j2 separated enough, then these observations should be independent or very close to independent. So we might expect something similar. And so for a sequence of increasing thresholds, you can ask, what is the likelihood? Likelihood now meaning, suppose I pick an initial condition according to mu in my phase space. What is the likelihood that my observations in a trajectory of length n don't exceed my threshold? And to obtain a non-trivial limit, you can increase these Zn up to the maximum of your observation. Okay. Again, we want to have this scaling, so the this probability of exceedance here. This is analogous to this. And before we had t on n, so we want to do the same thing. So we can write this as lim n times this goes to some t, for some fixed t. And then in the deterministic case, Keller made a really nice spectral way of approaching this problem based on the differentiability of the leading eigenvalue of a, not exactly twisted, but modified transfer operator. And so what was shown was that this converges to e to the minus theta t, where theta depends on where this maximum occurs. So if the maximum of your observation occurs at some aperiodic point, then you're very much like the IID situation, because you have your trajectory, it's going around chaotically. There's some maximum of your observation, but if you happen to pass by it, because that point was aperiodic, you'll just typically keep going. And it's just like, it acts like the IID situation. On the other hand, if your maximum has a period of p, then what's going to happen is if you come really close to this point that has the maximum, then it'll take you a little while to go away from it, because the point's periodic, right? And so you might expect a slightly different extreme value law, because this periodic orbit is sort of sticky. Once you get close to it, you have to expand away from it. And so you have this adjustment to the theta, which depends on the total derivative around the orbit of the periodic C. So there's this dichotomy of whether the maximum occurs at a periodic point or a non-periodic point. And the way this is done is that you identify this exceedance set with a hole in the state space. So this is the connection back to open dynamics. So with this identification, the likelihood of not observing an extreme after n iterations is the probability that you didn't hit the hole yet after n iterations. So there's a complete matching of these, and in fact, the way this is proven is to go back to develop this linear response here for, now lambda epsilon is the leading eigenvalue of the open transfer operator we had before, where the hole has a size epsilon. So we have this tiny hole, which is the set on which we exceed the threshold. And what you're asking is, as this hole size varies, how does the leading eigenvalue vary? How does the leading eigenvalue vary from 1? If you shrink down to just a point, then you have the Perron-Frobenius operator. Your eigenvalue is 1. As you start to grow the hole, that value 1 will decrease. What's the rate of decrease? This is what is used. Okay. All right. So I'll say a bit more about the random setting. So in the random setting, we have the same kind of setup that we always have. We have this map cocycle. We have our random invariant measures, and we have a random observation, which, anyway, the random observation is called H. It's just like the G I had before. And we're going to start with some x and some omega. We create a random orbit, and we observe along it, updating, of course, the H to the particular fiber that we're on. So if we iterate j times the cocycle, we should observe with H sigma j omega. Okay, and we're interested in the extreme value law for this collection of numbers, random numbers. More precisely, we want the limiting law of the likelihood of choosing an initial condition, so that as we randomly iterate and randomly observe, we stay below these random thresholds. Okay, so a lot of randomness here. I already mentioned, I think I've motivated now why the randomness here and why the randomness here. But why the randomness here? Well, okay, here's one of my favorite examples. So, that's because you came late. Sorry. That's not my fault. That was, but do you remember Steve's talk where he was talking about observational and dynamic noise? Yeah. Yeah, there's observational noise. Yeah, yeah. So like the dynamic noise is in the T omega, let's say, and okay. Or it doesn't have to be stochastic, right? It could be some it could be some temporal bias in the measurement device. So as omega proceeds in time, maybe the measurement device has some, sorry, it's meant to be a joke. Okay, now where was I? Oh yeah, why the randomness in the thresholds? Let's say the observation is surface ocean temperature, to stay with oceans. And if you're a climatologist, then what is an extreme ocean temperature will depend on the season. Okay, if you're in winter, then even an ocean temperature of, I don't know, depends where you are, 23 Celsius, that might be an extreme temperature for somewhere in winter. Doesn't sound very warm, right? But what is an extreme temperature in summer would be much warmer. So in order to talk about likelihoods of extremes and anomalous statistics, you need to be able to adapt the threshold to the current configuration of the system. So you could, I mean, if you're a statistician, they talk about seasonally adjusted statistics. So that, like, unemployment rates are seasonally adjusted. Yeah, so you adjust your thresholds depending on where you are in the system. So that would be an argument for why you need to have an omega here. If you're a marine biologist and you're worried that the water is too warm for some kind of fish, then the fish doesn't care whether it's winter or summer, it just cares how warm the water is. And so that would be an argument for not having an omega there, to have an absolute threshold.
That's absolutely true, but for example, there are processes in which Z itself would have a different random process than H. I mean, the randomness in H and randomness in Z.
Okay, I can just product my random process and...
No, sure. I think there would be more.
Okay. Thank you for the comment, but I think we can incorporate this here because sigma is very general and it just should be ergodic, and then we can... Okay, yeah, that's a good point, thank you. I should try to incorporate that in future talks, thanks.
Actually, there is a really nice example. Network security. So you have these processes where people are sending emails and doing stuff like that. Everything depends on the time of day. So you do have randomness in the sense of sending an email at 3 o'clock in the morning. It's unusual, but it might happen. 3 o'clock in the afternoon is more common. You have that randomness. And then you also have the randomness of the type that you have defined, but that randomness in the threshold is really dependent only on the time of day. Like 3 o'clock at night, sending a megabyte size file might be a lot. 3 o'clock in the afternoon might not be a lot. So they are different.
Okay, you're saying like file size is one thing and time of sending is another thing. Okay, thanks. Yes. Okay, so now to get an extreme value theory for random dynamics, we'll make this same connection with open dynamics. So the sets in the phase space where the random observation exceeds your random threshold, this corresponds to a random hole. So you now imagine when you have your random dynamics, it's not that you have to have a fixed hole in your phase space, but the hole itself can move around in time. So you have your random mapped cocycle, and on each omega fiber, you're free to have a completely different hole. And the hole itself may be a finite union of connected holes. Okay, so you may think of this random set of points in phase space where your random observation exceeds your random threshold as a random hole, and there's an n here, so these n is always going to always increasing, and the z's are also increasing with n. And so this epsilon n here, the notation is meant to say that as n increases, epsilon n goes to 0, and the hole size should in some way decrease. Actually, it will decrease according to the mu omega measure. Okay, so what we're interested in is the mu omega measure, the likelihood that we choose an initial condition so that we don't see an exceedance of the threshold. We don't see one of these random extreme events in an orbit of length n. and that is exactly the same as the likelihood you choose a point that is in the n-step survivor set for this sequence of random holes. So we turn this back into a problem of random open dynamics. And so the, okay, here's the statement. I think don't worry about this too much. This is just putting some uniformity on the invariant densities of the open and closed dynamics. This is something about that. It's like a weaker form of quasi-compactness. This is the Q we had before that had spectral radius less than the essential spectral radius or index of compactness. So the main things are, you have this scaling. The scaling is now random. So the T, previously it was a number. Now it's a, well, I guess it's a capital L infinity. It's in L infinity of P. So it's a random, it's a function. It depends on omega. Don't worry about the etas here. This is just some slight adjustment that slightly expands what you can do. And the main result is that this limit that we were interested in has this explicit form, or somewhat explicit form. So the T's here are the scales that you get to choose yourself. The thetas have a kind of long and complicated formula I'm not writing down here, but they're the random analogs of the Keller theta that had this fairly simple representation in terms of periodic or non-periodic orbits. And you average this over omega. So in the end, you have some non-random extreme value law because of, again, of the ergodicity of the base. So compare this. Here I'm reminding you what the Keller result was in the deterministic case. So we have this equals this, and he had this equals this. So hopefully you can see the analogy there. We put a bunch of omegas around the place. What was not so obvious is that here you have e to the minus t theta. Here I guess there are a few ways you could guess what would happen, but what the appropriate thing to do is you take the expectation of the t theta, and that goes inside the expectation. Right. So let me sketch. I think I'm still okay for time. Let me sketch how the spectral calculations enter this. So this is the target. I mean, I'm putting Lebesgue here, but this mu is going to be absolutely continuous, so the same thing, or easily convertible. So we want to estimate this. We write it like this. This is just, I'm just rewriting it with indicators now instead of sets. Then there's this trick where you use the fact that the Perron-Frobenius operator preserves Lebesgue measure. So I'm free to plug in here as many iterates as I like because it doesn't change the integral. Then you look at this and you say, oh, this looks familiar. This is, if you remember so the open transfer operator was, yeah, okay, I guess. So in this notation, L omega epsilon n acting on some f would be L omega acting on indicator of the complement of the whole at omega f. This would be the one-step rule. And turns out if you iterate this equation, then what this is just n iterates along this co-cycle with the open operator. So very nice. And so what you want to evaluate this number, right? So how is this going to grow? This is going to grow like the top Lyapunov exponent. So it'll grow like these are the multipliers. It'll grow like this n-fold product of these multipliers. This is some number that goes to 1. This is a probability measure, or very close to a probability measure. And then you have the lower order terms coming from the other Lyapunov exponents, which decay much faster. So the tricky thing is to evaluate this, because it's tricky because as epsilon n goes to 0, the lambdas are getting closer to 1, but at the same time you're raising them to higher powers. So it's a little slightly subtle. What you need from the random perturbation theory is something like this. So one of these things at each omega fiber, you can show that this goes like this. This is first order in the size of the hole. This hole will be small according to mu omega. And this is, if you like, the derivative, the rate of change of the eigenvalue with the hole size. Again, to first order, I can just by Taylor call this an exponential for convenience. And now this is for one of these guys. What I need to estimate is this product along a random orbit. So now imagine you have a product of these things. So you have a product of exponentials. So that'll be an exponential of a Birkhoff sum along the random orbit. And now remember we had this scaling here. So if you plug in this t omega on n to here, you'll get t omega theta omega with n. And now maybe the Birkhoff sum is a little clearer, and so in the large n limit, this is where the integral t omega theta omega comes from this product of exponentials along the random orbit. So this is the general scheme. So the ingredients, or a few ingredients, I guess, there's the Lyapunov exponents, you need this perturbation theory, and a non-standard Birkhoff. Okay, so now I think I'm still doing okay. I have 15 minutes, so yeah, maybe I could even pause for questions. I think I'm doing pretty well. Any questions? Okay. So now I want to go beyond this to, so what we did with extreme value theory was we said in an orbit, you have your observation, you have your threshold. In an orbit of length n, what's the likelihood you exceed the threshold? Now what I want to do is ask how many times you exceed the threshold. So instead of the trajectory falling in the hole, so if you see a threshold, you say, okay, I'm done. That was the previous situation. I fell in the hole, trajectory terminates. But now I want to think of exceeding these thresholds as just targets that the random trajectory hits. So if you hit the target, you get to keep going, and maybe you hit the target again and again and again. What's the hitting count distribution? So back in the deterministic case to start with, so we have our piecewise smooth expanding map. We have a decreasing sequence of targets. They're going to decrease like t over n. And we're interested in the following limiting distribution. So you you pick a point, you start iterating it. If it lands in the hole, the indicator is 1, and so this is counting, did I land in the hole j times? And what's the likelihood of that? So that is a distribution on the integers. It's a distribution on j. And then you want to know what happens as n goes to infinity. So in principle, j can be an integer from 0 to infinity. So again, let's think about a really simple case. Let's just say that for some stochastic process, not necessarily a deterministic map, for some stochastic process, let's say you're just trying to hit this target, and your success probability is t on n, and your failure probability is 1 minus t on n. And let's just say this is Bernoulli, okay? And you get n attempts, because you get n attempts. So now what I'm describing is a binomial process. Right? You have your success probability, and you have a certain number of attempts. So success is t on n trials, and as you know, this for n to infinity, this limits to a Poisson distribution with parameter t. So we might expect in the deterministic case, if we have a chaotic map and the target is not around anything special like a periodic point, we might expect to get a Poisson distribution, and that is what happens. So you can show that if the holes decrease to a single point, and that point is aperiodic, then the Zn converges to a simple Poisson with parameter t. Okay, very nice. Just to connect it back to what we had before, so Z Zn of 0, okay, Zn of 0 here, this would be the likelihood that you don't get an extreme event. Yeah, so just to slightly put it in context again, what we're doing here. Okay, slightly more complicated example is you could say, okay, what if your targets are centered on a periodic point and shrinking? Then, as I was saying before, if you come near the periodic point, then you're going to take some time to escape from it. And so you might expect that if you come near it, you might get a jump or a cluster of hits of the targets because of this. And so this is also the case. So you can show then that what you limit to is not simple Poisson, but you converge to a geometric Poisson with these parameters. I mean, this is not, I mean, I always forget the formula for these things, but the main thing is you have your t and you have your alpha. And the alpha is again related to, or is exactly the 1 over the derivative accumulated around the periodic orbit. So it's analogous to what was in the Keller expression. Yes?
It seems independent of the particular nature of stability of the period. So it's a saddle.
Well, it's one. I mean, it's 1D. So.
Oh, this is just in 1D.
Yeah.
Oh, sorry.
Yeah. And so this completely characterizes it as being unstable.
The potentiation, if we did this in several dimensions.
Yeah, expanding probably. Yeah. For expanding, yeah. I mean, you could, yes. So let's see. I have to think a bit more about the hyperbolic case, but expanding should be fine. Yeah. All right, where was I? Oh, yeah. So what does geometric Poisson mean? It means that your z looks like this. So you pick some x. These are IID, so the x should be distributed according to the geometric distribution, and you sum them up where n is Poisson distributed. Okay, so if we come back to the case where x naught was simple Poisson and x naught was aperiodic and z was simple Poisson, then you could write a simple Poisson process like this. You could say, well, it's just the sum of ones where n is Poisson distributed. And so you could think of this as a cluster size of 1, whereas the xj's here describe the cluster size where you have the this slow escape because you have a periodic point. Okay. More generally, you can show that these Zn's converge to what is called a compound Poisson distribution. So a compound Poisson distribution looks exactly like this. It's just that the xj's don't have to be geometrically distributed. They can be any distribution. Okay, they should be independent and IID, but any distributed how you like. Okay, so to show this spectrally, we're going to use characteristic functions in the probability theory sense. So we want to compute the characteristic function of Zn, which was SNN, where this is our counting function. And so we're going to use Levy's continuity theorem. So this will say that if you take the characteristic function of SNN, which by definition is this, and I'll denote these characteristic functions by var phi, they're a function of S. They're a little like a Fourier transform. So you have, this is your transformed variable. And if you have these things for a sequence of random variables in n, if you have these things converging pointwise to some phi, and phi is continuous at 0, then you know that Zn converges in distribution to some other random variable z. So this is what we're going to do this through these characteristic functions because it's going to be very convenient for the spectral approach. Okay, so let's see how this works. So we need a slight modification of the twist we have had before. So we have this twisted version of L. We define it by taking our argument. We now do e to the is indicator on the whole, and then the closed, the usual Perron-Frobenius operator. notice again, if S is 0, then you're back to your usual Prof operator. If you iterate this, then, so if you iterate n, L, N, S, k times, then what you pick up in here is not just indicator on the whole, but you start to pick up this SNK that you're interested in. So this is key point. And now this characteristic function, which by definition is this expectation, we may write like this. I'm just rewriting the expectation. Mu has density phi 1. Again, I play this trick of just inserting in here k iterates of L, because the Prof operator preserves Lebesgue integrals. So I can just plug this in here. And I think that should be an n, actually. This should be an n. And now I look at this and I say, oh, this looks kind of what I had before here. This is just n iterates of my twisted operator acting on phi 1. So now the question is, how does this thing go with n? And we're going to use, again, we use the quasi-compactness, and we use an argument similar to what I was sketching earlier. This kind of argument, a version of that, to control these. So you can show that this phi n is converging to some function pointwise. Okay. Yes.
How do you know that you have a spectral gap twisted?
Because I started with a spectral gap for the untwisted one.
Okay, but so even though you're multiplying by a complex number,
Yes. Yes. In my lecture yesterday, I don't know if you were there, I said that this is a very nice perturbation, and because it's analytic, you're just multiplying by an exponential. So yeah, quasi-compactness is, everything is behaving very nicely. Yeah. It's a much nicer perturbation than the Keller-Livrani type perturbations.
But I mean, what's to stop you from another?
Quasi-compactness.
No, that's not like discrete spectra. So you have inside you have a circle, the eccentric spectral radius. I can accept that doesn't change, right? But then
it does, but not, yeah.
Yeah, okay, but no.
This is all for sufficiently small s, right? So
Sufficient.
yeah, I'm not saying s can go as, yeah, it's all for sufficiently small s. And that's all we care about, because yeah, we're always looking at the limits of, yeah. In fact, we only need here that, where is it? We only need, by Levy, we only need the continuity at s is 0. So in order to show that, you just need to say something local to 0. Okay, so in the random setting, I want to do something analogous. You can probably guess what this is. So now I have a random sequence of targets. I have my random trajectories, and I want to know what's the likelihood that my random trajectory hits targets in this random sequence j times. What's that limiting distribution? So this is my random counting function. I have to, if I iterate j times randomly, I have to make sure that I have the indicator on the right hole. And this is the corresponding counting distribution. For, what am I saying here? Let h, I think I'm just reiterating what I said before. Yeah, you can connect this with random extreme events. So I think we covered this. So we have a random observation. I'm saying that you could, if you want to connect this with counting extreme events, you can define the targets by locations in phase space where you exceed the threshold. So that, I think we already discussed this. So we could define, again, the hole, the random hole, as at step n as the likelihood that, sorry, the set of points where you exceed your threshold on fiber omega. Okay, I think I have verbally said all of this stuff. And the way we're going to demonstrate the final result is we have a random version of the twist that we just discussed. So you have an L omega n s. You take your random Perron-Frobenius operator, you apply it to your argument f multiplied by e to the is indicator on your random hole. And you have this same nice cocycle property that if you iterate this twisted random cocycle k times, what you get up here is your counting function. And the strategy is essentially the same. So the result is that for your random perturbed system, the limit of these random characteristic functions for each, so for each omega, fix omega, you have the limit of these random characteristic functions, which is by definition this. This, like a partial step along the proof, is that you get this product, random product of Lyapunov multipliers, and that as n goes to infinity converges to some fixed non-random function with expression like this. So it's related to what we had before. In the extreme value case, we didn't have this. So it's not that much more complicated actually. You just have to put in this dependence on S, but otherwise it's the same as the extreme value case. And from this form, it is very easy to show that you are compound Poisson. That's like a one-line argument. And you can also, you can get expressions for the mean and the variance of the z that corresponds to the phi. So the phi is the characteristic function of some z. And we can also get expressions for the mean and the variance of the x's that you would make. So what I'm saying here is that this phi, it corresponds to a random variable big Z. And the random variable big Z is compound Poisson. That means that it's of the form like this, where this is Poisson, and these guys here are IID. So from the quantities like the t's, the thetas, you can get expressions for the mean and the variance of these guys, and the mean and the variance of these guys, and consequently that guy. Okay. And only went 1 minute over time, so thanks for listening to all my lectures. Like a question for me.
I mean, it could be. So I mean, like, yeah, I guess is there any cases where you're interested in like the, like meaningfully twisted operator, like you have S where there's a large number.
Meaningfully twisted.
Well, like not just a small perturbation, but like an actual larger perturbation.
Are there any? Is there anything interesting about that? Is your question?
Well, I mean, is there anything interesting? I mean, I guess they turn up in whatever like continuous time systems, but like, do they turn up?
Do they?
Yeah, like if you have like a suspension, like a Poincare map, right, and you want to look at the eigenvalues of a transfer operator. So you have a continuous time system. You want to look at the eigenvalues of a transfer operator, or like whatever, like resonances on this system. You look at the Poincare section, and the eigenvalues are like based on solving one of these, like finding values of S where this twisted transfer operator has eigenvalue 1. But I mean, I'm just like, do they turn up in statistical laws anyway?
I don't think that I know that, so I cannot answer your question. Sorry. Yeah, I mean, in these statistical limit laws, it's always for small s, and I'm not aware of an application where you would get something. Maybe I'm forgetting something, but I cannot think of an application where you have some large s, and then that tells you something about the dynamics. If that's your question. No, even local limit laws, I think you have to be more careful with. I mean, well, I'm not sure. Nothing comes to mind at the moment.